When most people hear the word ergonomics, they picture a very expensive office chair. It's usually marketed as a luxury feature for knowledge workers trying to avoid a stiff neck. We're told it's about tweaking the lumbar dial or calculating the exact distance between our eyes and the computer monitor to reduce daily strain. But treating ergonomics as a corporate perk ignores the actual origins of the science. The discipline was built to address the high-stakes, physically grueling conditions of heavy manufacturing and manual labor. Historically, and today, some of the highest-risk environments are found in places like meatpacking and poultry processing plants. Here, workers repeat the same forceful motions thousands of times a shift, pushing human tendons and joints to their mechanical breaking points. The danger is equally severe in healthcare. A major source of physical trauma involves nurses and aides executing heavy manual lifts to move patients in nursing homes. During the Industrial Revolution, early factory production relied entirely on human power. Workers were forced to adapt their bodies to machines that were built with zero regard for human anatomy, creating massive efficiency gaps and rampant injuries. Ergonomics serves as a mandatory engineering discipline, hardened to prevent the human body from structural failure under industrial workloads. For decades, the workplace was entirely task-oriented. The machine was fixed, and the human had to bend to fit it. Modern ergonomics reverse that model. It requires the technology and the task to fit the user. The International Ergonomics Association explicitly defines this as a scientific discipline. It's the study of the interactions among humans and other elements of a system, optimized for overall system performance. To execute this, engineers pull from a strict multidisciplinary framework. You cannot design a safe factory line without integrating biomechanics, kinesiology, and human physiology. The primary physical threat this science seeks to eliminate is the work-related musculoskeletal disorder, or WMSD. These are entirely different from acute workplace accidents. If you suffer a chemical burn or a sudden fracture, the cause is immediate and obvious. A WMSD starts as localized fatigue and strain. It is the soreness in a joint that simply doesn't recover after a night of rest. To prevent these injuries, safety engineers can't rely on subjective complaints or wait for a worker to say they hurt. They must quantify the biomechanical forces acting on the human body using objective data and physics. The medical understanding of these injuries evolved alongside industrial science. Early diagnoses were highly specific, like carpal tunnel syndrome, before broadening to repetitive strain injury. Researchers realized these issues resulted from chronic accumulation of microscopic trauma, leading to the modern classifications of WMSDs. Carpal tunnel syndrome serves as the classic foundational example of how this cumulative trauma operates. This anatomical cross-section of the wrist shows exactly what happens. Repetitive motion causes the flexor tendons to become inflamed. As they swell, they compress the median nerve against the transverse carpal ligament, resulting in severe pain and loss of motor function. But cumulative trauma isn't limited to the wrists. The exact same mechanical wear and tear degrades the neck, shoulders, and highly vulnerable structural points like the L5 vertebra in the lower back. These biological failures do not happen randomly. They correlate directly to measurable physical actions required by the work environment. Because these disorders are physical, their onset is entirely predictable, provided we can accurately map the forces acting on the worker over time. To engineer a solution, we must break down a hazardous task into its distinct risk factors. Take this standard industrial scenario, a worker manually lifting a heavy, awkward machine part from the floor. The first variable is force, the physical effort to overcome gravity. Next, repetition and static posture measure how often and how long muscles maintain a load. Finally, awkward postures. When a joint leaves its neutral alignment, mechanical tissue stress skyrockets. Simply identifying these physical hazards is not enough. Engineers require a mathematical model to calculate how these specific variables interact to cause tissue damage. That requirement led to the NIOSH lifting equation, the premier mathematical framework used by safety engineers to evaluate manual lifting risks. The formula calculates the RWL, or recommended weight limit, the absolute maximum safe weight for a specific task. We start with the LC, the load constant, representing the maximum weight a person could safely lift under perfect physical conditions. Every other variable in this equation is a multiplier, expressed as a fraction less than 1. They act as penalties, reducing the safe lifting limit based on the imperfect geometry of the actual task. Look at the HM, the horizontal multiplier. This measures the distance from the body's center of gravity out to the hands holding the load. This schematic demonstrates why that distance matters. Reaching further outward increases the moment arm. This leverages the weight of the object, multiplying the compressive force on the lower spine exponentially. Then there is the VM, the vertical multiplier. Starting a lift too close to the floor or ending it above your shoulders puts you outside your body's power zone, dropping the safe weight limit. The equation also applies an asymmetric multiplier if the task requires twisting the torso, and a frequency multiplier based on how often the lift happens. The NIOSH equation reveals that the true biological load of an object fluctuates wildly based on the specific geometry and physics of the lift. Calculating the recommended weight limit gives us a baseline, but it's only the first half of the ergonomic assessment. To measure the actual hazard, engineers calculate the lifting index. You take the actual weight of the load being lifted and divide it by the recommended weight limit we just found. The critical threshold is 1.0. If the calculation returns an index greater than 1, the physical demands of the task are mathematically proven to exceed human anatomical limits. Operating with an elevated lifting index is a guarantee of system failure. It flags an environment that is highly likely to produce cumulative trauma, specifically crippling lower back injuries. Once a hazardous index is verified, the engineering priority immediately shifts. We stop measuring the problem, and we start modifying the system. The most common industry response to a dangerous lifting task is simply to tell the worker to use better technique. Keep your back straight, lift with your legs. But true ergonomics doesn't try to adapt the human to a flawed task. It changes the physical variables of the task itself. Look at this comparison. By simply raising the starting height of the materials from the floor to a table, we instantly remove the awkward bending posture, eliminating the vertical penalty from the NIOSH equation. The ultimate solution is deploying mechanical engineering controls to reduce the spatial penalties and the load weight to 0. This is why facilities use scissor lift tables to adjust vertical heights on the fly, and hydraulic pallet jacks to remove the heavy force requirements of moving stock. By introducing these tools, engineers physically manipulate the variables inside the lifting equation, artificially lowering the lifting index back down to a safe level below 1. Protecting a modern workforce requires the rigorous application of physics and biomechanics, using empirical data to safeguard human anatomy. We use empirical data and mathematical formulas because they are the only reliable tools we have to bridge the gap between biological limitations and intense industrial demands. When we design the workplace to fit the biological realities of the worker, we aren't just preventing injuries, we are optimizing the performance of the entire system.